Hello, everybody. Welcome back. Do I have a? Yes, I seem to be having my sound. Just double checking. Welcome back to another catastrophe that is a deep astronomy live stream. My name is Tunya Darnell. See, I figured it out. Well, my green screen's screwing it up. That's what I want you to call me now, Tunya. From deep astronomy. Deep astronomy. Anyway, God knows what's going to happen in this next hour. The whole universe could end. The world could my stream will most and definitely have technical issues. So it's gotten so bad. Even Hans Milling, which hello by the way, has to make sure he lets me know that the sound is fine. So yes, because that's where we've been here, folks. We have been through the ringer, as they say. Anyway, wow. I don't know about you, but I'm a little bit amazed that the James Webb Space Telescope has gotten as far and as it has as quickly and as flawlessly. None of us would be thinking that. Remember back a couple weeks ago, we're all like, "Oh my God, what if it doesn't deploy? Oh my God, we're gonna have all these problems, and it's just gonna set back NASA back 20 years if we don't deploy this thing." Man, not only did it deploy, but it did it just absolutely with no hitches at all so far. Knock on wood. So let's not worry about this. NASA's got this. I'm pretty amazed. We're going to check in on where it is right now at this moment. But now we're like, oh, yeah. Yeah, it's like Ryan. Yeah, they knew they would get it all along. We all knew. We all knew. Yeah, we knew we had this bullshit. We were crapping ourselves and we know it, right? So yeah, we're doing fine on this effortlessly. Yes. You know what I think we should do? Because I'm in America. Hey, Ebone, it's good to see you. By the way, all those delays are paying off. I don't know about that. I mean, that's going to be relative. Man, that's a relative statement, right? Are they paying off? Well, I think so too. But it costs a lot of money. It costs a lot of money to get us where we are right now. So I mean, I guess they're all paying off. So knock on beryllium. That's right. That everything is going to work okay. So far so good. You know what? Because I live in America and today's January 6th, we live in a world where, it's easy to say things that aren't true. What if we all started? Now this will be mean, but this goes to show you just how sick my mind is, right? What if we all start the rumor that NASA didn't really launch Webb? That it really didn't go off? We don't need that headache. I'm a science communicator. I shouldn't be promoting this, but let's do it. Let's say, NASA didn't really do this. They didn't really launch the James Webb Space Telescope. Really, what they've built for this $9 billion is a getaway spacecraft for the rich and famous. So people like Elon Musk and Jeff Bezos, this is what they're going to use to get away. I said that in joking last night, and Charlotte was like, "Oh my God, you have no idea how many people would probably actually believe that." So let's don't do that. So greetings from Norway. Hey, thank you. It's good to see you. I'm glad you're here. I love your name, by the way, Los. I like that. I just have to show you because last week we went through this. Look what I figured out how to do. This is my new name. So I have all kinds of special characters in my name now. I'm even going to use the AE, which, by the way, I couldn't figure out how that's actually pronounced. It could be pronounced EE, like deep astronomy, or AE, or A, like encyclopedia. You could say encyclopedia or encyclopedia. So it's kind of a lots of different ways you can pronounce that. So in the context here, it's deep astronomy. So yeah, I'm on board. I want special characters in my name. I feel a little bit left out, so that's what I'm going to be calling you now. I think it's pronounced Tunye, Tunye, Tunye. Yes, that's what I want you to call me now. So good. And uh that's a little bit of an aside. Yeah, Stanley, Stephen, I'm sorry. There are no cameras on board. So yeah, I'm going to talk about that in just a minute. Why there aren't any cameras on board? Because I found a pretty cool answer to that. But yeah, could you imagine? They could be anywhere, right? Did it really actually launch? We could probably get away with that, and a lot of people would probably believe it. the world we live in, man. It's just the world we live. You can just say stuff, right? Um, so, um, Sarah's commenting, people have been talking about Don't Look Up much recently, but have you seen the movie Stowaway? And what do you think about the science in it? I have not seen it, and where can I see it? I will watch it if you tell me where it is. I saw Don't Look Up on Netflix. I thought it was a great movie. It made me laugh and cry all at the same time. It was, I thought, very it brought a lot of issues home to me because of how science communication and trying to trying to get ideas and science across is a little bit hard in this day and age. So I love Don't Look Up for the points it was trying to make. Ireland, Brian, thank you for joining. I'm going to Ireland hopefully pretty soon, maybe in February, because I play the Irish whistle, and I'm going to be playing. I want to go play in some pubs around Galway, especially. So, welcome. I'm glad you're here, and I can't wait to get to Ireland. Hello, Ireland. that's from that's from the Seremes. Okay, so let's find out where we are on James Webb. Today, I want to talk about the observations. Right, we have really gone quite far in the deployment process. There is a lot still to go through. But where we are right now, as of today, is right here. This is the world's famous deployment uh, explorer, if you will. And where we are today is this aft deployment instrument radiator. This instrument radiator deployed today. And so we have a spacecraft that looks kind of like this right now. The tensioning has already been complete on the sun shield, sorry. And things are looking really good there. That was a big nail biter. That was the part I was really concerned about because that didn't go well during testing. And that was the one part of the telescope that you can't test on the ground very well because this was going to be deployed in 0G or in micro G, and this was the only way you could test it was on Earth. So it wasn't, but they did a great job. Not only did it deploy, all 5 segments were tensioned and separated, and of course the secondary mirror has gone down. Now, in my opinion, if nothing else happened, nothing else went right, you could still use this telescope from here on out. You've got secondary deployed, most of the primary is there, and so you can use this telescope in its current configuration. So that's where we are right now. What's coming up is this part where we're going to the primary mirror wing is going to be unfolded. Now they've actually put a date on this. They're going to do it tomorrow, it looks like. So that part happens on Friday. Then they're going to, again, they're going to, fully latch it in place, and then they're going to do the starboard side on Saturday. So by Saturday evening, we should have this. We should have Webb is fully deployed! Exclamation mark. Now, when NASA uses exclamation marks, that's a big deal, right? So Webb is going to be fully deployed 2 weeks after launch. Launched on Christmas Day, as most of us know. So there is the schedule of where we're going to be on the deployment. But in order to talk about observations, which is what I want to talk about today, we need to understand that we got a long way to go before we're ready to take science observations. The deployment's the big part, right? And this is without a doubt the most complicated deployment I think that's ever been done remotely, and that includes the Mars lander 7 minutes of terror stuff. Yes, that was complicated. A lot happened very quickly. It was amazing. This, however, I think dwarfs that in terms of complexity. And, kudos to NASA, man. This is like, wow, you guys had this. You guys had this. So no worry, I think, on the deployment part of it. I mean, they're still, of course, clenching various sphincters to make sure that they won't rest until this day happens, this Saturday. But they've only got a couple days left, and it'll be fully deployed and ready to go. Not quite. Not quite. Why? Because you have to commission it. And oh, let me just point out a couple things here. This you want to follow the blog. As Uncle Bill pointed out on my Discord server, the Deep Astronomy Discord server, which you should join. Its link is in the thing. The um, they're really good at right away after something happens, telling you when it happened on the blog. This right here takes has a bit of a delay in it, but this is pretty quick. And as I was looking at this, I always go here like Uncle Bill does to verify that it happened. I saw this. This was a post they just also made today, answering the question, why doesn't Webb have deployment cameras? I'm not going to read all this to you, but the short answer is they tried that. They thought about it. They wanted to they wanted to put deployment cameras on there so we could see what's going to happen and where it was. But then but that's not easier said than done. There's a hot side, a cold side. There's also a shiny side, which is all over the place. So where would you put the cameras and how many? And the operating environments for each camera would be very different. For example, to put a camera on the hot side, the side facing towards the sun, would have to have operate at a much different temperature than the ones on the cold side, which would need to get down to cryogenic temperatures. This thing's got to get down to 30 Kelvin. So these cameras have to work really well there. Not to mention all the cables for the cameras themselves would have to be stretched across surfaces that were very critical to the mission. And because the way they designed Webb, this was a one off telescope, and the engineering data that they needed to know when certain things had deployed, locked into place, all of that kind of stuff, they had actuators and telemetry sensors for all of that stuff. They didn't need the cameras, they had all of the engineering data that they needed. A camera wouldn't have added that much. The kind of imaging they would need to have done would have to be, in some cases, really high resolution, close macro scale uh, lensing, and in other cases they would need wide field to see the whole thing. In which case they wouldn't get much detail at a granular level if something went wrong. So it was determined that because of the complexity of adding cameras on board Webb, they didn't do it because they didn't need it. They could get that information everywhere else. Now, as many of you have pointed out, some of you anyway, already, that the that the um, conspiracy theorists are going to have a field day with no cameras. How do we know that the Webb actually deployed the way they said? So that's a problem. Not really, but anyway, I thought that was a good answer. If you want to, here's the blog. Go look at it, read it yourself. I'm going to put this in here, and it should be on all the things now. By the way, I'm streaming on Twitter, Twitch, Facebook, and YouTube. So I'm on those things, and I'm seeing all of the different different things. No, that's not what I said. Analytics group. Besides, that's a funny name. Um, it's not too complicated. It is the level of complexity that would be required to add all of these cameras, and then we're not talking about slapping on a Nest camera or a ring camera on a space telescope and calling it good. If you think that's what's involved, then maybe you might want to rethink this, right? I mean, if in order for these cameras to provide the information that would be needed to have a camera on there in the first place, the added complexity of putting the cabling, the cameras, and all of that kind of stuff was just deemed unnecessary. Now, a lot of people will be the first ones to complain. Oh, well, let's just spend another $100 million on webcams to put all over the Webb Space Telescope. People will be complaining about that soon enough, right? Because well, what do we need webcams for, right? So you can still pleasing everybody, but of course, it's not too complicated. It's just that they could do it, but it was unnecessary. The level of complexity required to put it on there, it was deemed unnecessary because they got the telemetry and engineering data they needed without them. Not too complicated for NASA. I'm defensive now because, they've done an amazing job. I don't want to hear anybody talking crap about it. Okay. um, So I'm just reading some of these chats here. What about sending another mission primarily for cameras that can film the JWST whilst doing its mission? I I guess. I mean, first of all, let's remember where it is. It's at L2 and it's dim out there, right? What are you going to do? Shine lights on the James Webb Space Telescope so you can see it? That's a lot like going outside with your telescope and trying to observe, the Orion Nebula while somebody's shining a flashlight in your face. Maybe not the best way to go. So, maybe let's don't do that. Uh, okay. No more chat. Right now, I'm going to concentrate on what I'm talking about. So, what comes? All right. So that's why Webb doesn't have a deployment camera. Let's talk about commissioning Webb. So after it deploys, it should be fully deployed by this Saturday. All things going the way they've been going. Uh, the telescope is going to head out. It's going to be flying around to the L2 point. Now, this schematic here uh, says that it will arrive at L2 at 30 days after launch. Now, this whole thing, this whole circle is one orbit around L2. So after it arrives, after it's been deployed, and after 30 days after launch, it's going to be here. It's going to arrive at the thing. Here, let's just go ahead and take a look at where is Webb. Webb is right here. This is the Earth over there, and over here is L2. And right now, it's in this spot as far as the distance timeline goes. So this is where it is. And once it gets to L2, let's switch to this. What's going to happen? Well, a lot of things. They've got us. The longest part of this whole thing getting ready for science data is going to be getting the instruments cooled and turned on and checked out. Not necessarily in that order, but here's the way they've got it outlined. It arrives at L2, and this green part of the loop is where they are commissioning the telescope itself, the mirrors, the adjustments, and all that kind of stuff. And then this part of the orbit is where the science instruments get commissioned. So there is a really good article written by Heidi Hamel that you should read. It's on planetary.org. And I got this from there. And it describes the whole commissioning process of the telescopes and the science instruments. So the JWST team will take 3 months to the first step will be to carefully align 18 mirror segments, and this will go very slowly. One of the telescope scientists described the mirror segments this way: they move about as fast at the same rate as a blade of grass grows. Right here. This delicate but time-consuming process brings the 18 separate images together to create one sharp image. So here in the commissioning process, these 18 mirror segments in the telescope itself are slowly being moved into place to create a sharp image. And that is where this whole from day 36 to day 120 is going to happen. So each step is outlined here. They're going to take an image mosaic at day equals 30 or at 36 days after launch. They're going to turn on and use the fine guidance sensor at 50 days, and then they're going to start moving the telescope segments around, and they're going to do this what's called coarse phasing and then fine phasing. This is getting them all all the mirror segments lined up. Then they've got to worry about the image plane. The image plane, this is example of what the image stacking is going to look like. There's the individual frames, and then these are going to be the fine control of the mirror segments. And then when it's finally set, it should look like this. Okay, the image number 4. At about 80 days after launch, they're going to start focusing the different images and getting everything nicely focused all through this green arc here. By about 100 days after launch, the MIRI, the mid-infrared imager, that's the camera, will be complete. It'll be cool at 100 days after launch. They're going to have multi-instrument activity complete after the 115 days. And now finally, after 120 days of commissioning, the telescope alignment, the mirror segments, the primary segments, the secondary, and all of the instruments will be in focus. Not every instrument will be focused at the same time. When Webb looks at something, this square rectangle is its field of view, and inside are these different footprints for the different uh, parts of the image of the imager, right? You're going to have near cam in the center, near spec off to the side, the mirror instrument, mid-infrared imagers will be off here. Near infrared slitless spectrometer is going to be here. 5 guidance sensors 1 and 2 will be focusing in this area of the image plane. This is where all of the instruments will be uh, um, aligned and set on the image plane of JWST. So when you want an image from near cam, you're going to be looking at this area of the field of view, just grabbing this is where, when Webb is pointing at something, the object will appear in that field of view. Okay, so now we're going to worry about the instruments. They've got they're going to be testing the fine guidance sensors. That's going to be the thing to make sure it's pointed successfully and accurately. They're going to be testing the pointing stability at 130 days after launch. The coronagraph on MIRI. This is the part there where you can block out the star and image exoplanets. That's going to be tested, and the positions of those are going to be worked through. They'll have a variety of observing modes from near cam. They're going to go through all of them. They're going to do the same thing with nearest, near cam, and MIRI. They're going to be making sure all of these instruments are working, and the solar system moving tracking, target tracking will be ready after this point, and then all of this stuff will be verified and ready to go by 180 days, 6 months after launch. So we've got until June or so to see this. Now, before we see this, now Heidi wrote that at the very earliest, the first science images should appear in June, though given the complexities I've outlined above, I would not be surprised to have to wait until July or even August. So the science data will be ready this summer. All the while, the cooling is happening. All the different instruments are being focused, aligned, and tested. That whole thing is going to take about 5 months after it gets there. So we've got a lot of work still ahead, and all of it is vitally important work. This is part of that 300 something single points of failure. I think we've gotten through about 250 of them by now with this deployment process. So that was a big one, getting things deployed. But now now everything has to be turned on, pointed right, and aligned. And that's what's ahead for the next 6 months until June. First light will probably be some kind of focusing image. We're going to probably see one of these sorts of images being released by NASA when it comes out. One of these sort of test calibration images. So it won't be anything of an object or anything like that. That's my guess. They may not release it, but I'd be shocked if they didn't. Okay, so that's what we have to look forward to in the commissioning process. But what we really care about is science. When are the science data coming through? And I thought I'd spend a little bit of time talking with you about the kinds of observations that it's going to take, and what they're going to be doing, look at some specific observations that they're going to be taking after the thing has been commissioned. So let's talk a little bit about scheduling. And I've gotten all of my information from the Space Telescope Science Institute website, stsci.edu. They are operating the James Webb Space Telescope. They are responsible for uh, deciding who and gets to use it and when and for what reason. And I wanted to read this to you, the scheduling of observations. So, how do you know when observations are going to be scheduled? And the prime criterion applied to scheduling JWST observations is maximizing the overall efficiency. Priority scheduling will be enabled for two different classes of programs. So, on they want to make sure that they don't move the telescope more than they have to. So all observations will be planned out in order of where the telescope is pointing and for the length of time that it needs to point, as well as what instruments are being used. So all of this has to be taken into account. But they will priority schedule under two classes of programs. Programs where there's a clear scientific justification for scheduling within a particular time window. For example, something pops up that they didn't know about, and the early release science program, where, as far as possible, observations will be scheduled within the first 5 months of cycle one. That's the first uh, cycle of observations for science, to provide the community with access to the data prior to the cycle two proposal deadline. So, cycle one observations that are going to require more observations for cycle two will also be prioritized. So, what kind of observations are there? And this, by the way, is coming off of a FAQ for science, FAQ for scientists, which I think is very interesting. You might want to read it yourself at some point. I mean, I'll just go ahead and put this there. That's this. And I wanted to read this to you. What are the policies and plans for observing with Webb? The policies for Webb observers will be very similar to those of other great observatories, with more than 80% of the available time uh, to those submitting general observing proposals. Those are called GO proposals. 80% of the time is going to go to those. An additional 10% of the time is director's discretionary time. That's important because DDT is what was used with Hubble to create the Hubble deep fields. No scientist wanted to waste their proposal on a deep field when they weren't sure they were going to get anything. So the director of the Space Telescope Science Institute used his time to take it. So all kinds of cool stuff comes out of director's discretionary time. While the remaining 10% of the first 5 years is something called guaranteed time. And I'll explain what all these are in just a minute. So 80% goes to general observing, 10% goes to director's discretionary time, and 10% is go in the first 5 years is called guaranteed time. And um, so let's look at what each of those means. General observing, that's just what you would expect, right? This is the observations and archival research proposed by the community and selected by peer review. Everybody who wants to use JWST puts in a proposal. They say, I want to use it and why I want to use it. And then if you're approved, they put you in the cycle for that observations. What's more, and a lot of people don't know this, you you also get money. They pay for that time. You get a grant. If you're in the US, a US scientist and institution doesn't have to pay for time on Webb. That's included in the NASA budget for operating the James Webb Space Telescope, which I thought was cool. A lot of people don't know that. The director's discretionary early release science programs. These are observations to be executed within the first 5 months of science operations and released immediately to the community. And then finally, there are guaranteed time observations. This is what we just talked about. These are observations that are defined by members of the instrument and telescope science teams, as well as a number of interdisciplinary scientists. These are this is usually done. These are observations. They're called guaranteed because they happen early in the mission. Webb's mission is nominally for 5.5 years, but as we've been learning, it's got enough fuel on board at least to operate for over 10 years. Let's hope it goes that long with nothing else going wrong. The one limiting factor that was going to be on James Webb uh, project lifetime was the amount of fuel on board. But because the launch was so good, went so well, they got extra time. So they got extra fuel. So, assuming nothing else goes wrong, they're going to have over 10 years of mission life in the James Webb Space Telescope, at least as far as the fuel goes. So, these are the kinds of things. Oh, and there's also calibration programs. These are observations where they just have to calibrate the instruments. They have to take data to support keeping the instruments calibrated so that when you get your data, you actually know what it means. So those are the kinds of observations that are out there. And I can tell you, that I'm most excited about the director's discretionary time. This is something I'm really glad they built in, because they have this uh, flexibility to do things that maybe Webb wasn't quite designed to do, but would still have a great scientific case for. But gosh, gee willikers, I'm a scientist and I don't want to spend my time on this. So would you spend your time on this? It's really it gives a level of flexibility to observations, I think, for Webb that wouldn't ordinarily be there. So it's 10% of the time. Um, so let's So that's the kind of time that Webb allocates. The way they choose time is there was another part. Let's see if I can, if I can't find it quickly, I won't, oh, yeah. So there's a fact on observing solar system objects. And in reading that, I came across this statement. One of the frequently asked questions is, how do I get observing time? And the answer is write proposals. The JWST proposal process is similar to HST's. The JWST Science and Operations Center will be located at the Space Telescope Science Institute in Baltimore. The HST proposal preparation software already has hooks in it to support JWST protocols. If I have time, I'll show you that in just a minute. But of course, it's not ready yet. It is ready now. The first proposals will be solicited about a year before launch. Competition will be fierce. And here's the cool part. Money will be allocated, or money will be awarded to successful proposers from U.S. institutions to support their analysis and publication of the observations. Pretty cool. So that's how you get observing time. But I can promise you, as you can probably imagine, it is going to be crazy competitive. So you're not just chances of getting it uh, pretty small. So before I get to some of the specific observations, let me read. I have to switch back and forth between telling you what I'm going to tell you and then reading the chat, because I can't concentrate on two things at once. So here's something from Will. I saw something that said Webb could see further back, closer to the Big Bang, and possibly detect primordial black holes. I thought black holes were at the other end of the UV spectrum in UV and X-ray. That's right. I will talk about some of the observations that Webb will make with black holes in just a minute. But if you think about where these objects are in the early universe, a lot of that wavelength has shifted into the red, is redshifted into the infrared, which is why it is the wavelength range that it has. So why does it take so long to cool these instruments? Because they need to get very, very cold. This is space, we know of it as being in a vacuum, isn't really completely empty. And it's also it's not always cold, right? Depending on where you are, the sun heats you up really, like I think the moon has a temperature range of over 100 degrees between its light and dark sides. So, there's a wide temperature range there. And these radiators and these sun shields that are on Webb are positioned in such a way to always keep the instruments pointed away from the sun out towards the deep cold of space. And there's even coolant on there to help maintain the 30-degree Kelvin range that it needs. That's hard to maintain in space. It needs to be cold, and it needs to be always that temperature, not up and down depending on where it's pointing. So space is an environment like anything else, and the temperature ranges are also all over the place. So it's um, so to get that cold, apparently it's going to take 5 months or so to get it there to that thing. So to that level anyway. Ryan, so we have plenty of fuel, but reaction wheels don't have a good reputation for longevity. I wonder how many systems are redundant in JWST. Boy, gosh darn it. I found the greatest answer to that question. Oh, but the question is, can I find it? Oh man, I wish I'd had that handy. Um, Um, Give me just a brief moment, as I found the exact answer to this question. Um, Ah, what is Webb doing to ensure that its gyros last the full mission? This is in that scientist fact I was telling you about. I'm reading from this page right here. I would show it, but it's on a different browser, and I don't have the screen share on that. So I'm reading from this page right here. Um, and it says the gyroscopes on HST and Chandra are mechanical devices dependent on bearings for their function, and they face problems typical of such designs. Webb has adopted a different gyroscope technology. The hemispherical resonator gyroscope, or HRG, uses a quartz hemisphere vibrating at its resonant frequency to sense its inertial rate. The hemisphere is made to resonate in a vacuum, and the hemisphere's rate of motion is sensed by the interaction between the hemisphere and separate sensing electrodes on the HRG housing. The result is an extremely reliable package with no flexible leads and no bearings. That's very important. The internal HRG operating environment is a vacuum. Thus, once the gyroscope is in space, any housing leaks would only actually improve its performance. The HRG eliminates the bearing wear out failure mode, leaving only random failure and radiation susceptibility of the electronics, which all such devices share and which can be mitigated by screening and shielding. Stress analyses of HRGs show this design has a mean time of failure, has a mean time before failure of 10 million hours. As of June 2011, this type of device has accumulated more than 18 million hours of continuous operation in space on more than 125 spacecraft without a single failure. So that's awesome, right? Um, and The reaction wheels. What kind of reaction wheel does Webb have? JWST will employ Rockwell Collins Deutschland, which GBMH, formerly Teldin. Oh, forget all that crap. JWST will employ reaction wheels. These wheels have heritage traceable to the Teldix wheels flown on NASA's Chandra, EOS, Aqua, and Aura missions. But it does not say the ones that were flown on Kepler. The one that was the one which um, failed. One of the reaction wheels failed, or two of them it did actually. As far as the reaction wheels that they've used, apparently are going to be fine. Certainly the gyros, which has been the issue with Hubble. Hubble has had 5 servicing missions. Every single time they've had to replace the gyros. And this last servicing mission, and all the problems that we've had recently with Hubble have all been related to their gyros because they're bearings, right? So the gyroscopes that are going to be pointing JWST are bearingless um, gyroscopes. So that's all good news. And I would point out that um, the SOHO spacecraft, which was launched in 1995, and it's currently sitting at the L1 point, has been up there since 1995, also has reaction wheels on board. Now, it only points at the sun, so it doesn't have a lot of pointing to do. But those, I think, are the same kind of reaction wheels used uh, on Webb. So that's a good question, though, and I was pleasantly surprised by those answers that I found in the facts. So, and I gave you the link in the thing. So, um, okay, a couple more questions that I'm going to get to this. Assuming the telescope dish is connected to the spacecraft through the center of the sun shield, um, what's to stop heat transfer through this central column? So there is a coolant. Well, first of all, there's this radiator that was just deployed, right? That this radiator. Um, Let me pull it up here. This radiator takes heat from the chassis itself and disperses it out into space. There's also coolant in here, which also provides an extra boost. So yes, there will be heat transfer coming from the column of the whatever's connecting the power of the spacecraft bus to the instrument and the optical tube assembly, but there are cooling mechanisms, and of course, it also has to go through those 5 radiating layers, which should help disperse some of that heat as well. That's the kind of question we need to ask John Ehrenberg or somebody who worked at Northrop, because I don't know the full answer, but there will be, and I'm sure that's been taken into account. That's a good question. Okay. So, um, did I have it wrong? I thought I said, did I say 30? Is it 7? Okay, maybe 7. I thought it was, I don't know where I got 30 from, but thank you. Okay, so down to 7, or very, very cold, right? So, um, I don't know the diameter of L2. L2 is a gravitational Lagrange point, and I don't know what their physical size is. If it's certain, I don't think it's a pinpoint, but I don't know the answer. But if you saw, as you saw in the deployment in this here, this commissioning, it is going to be in an orbit around the L2 point, but this isn't to scale, and it doesn't give me the size or the diameter of that orbit. Um, so that's all I know about it so far. Okay, I want to talk now about cycle 1. These are the actual observations that James Webb Space Telescope is going to do when it gets started. The General Observer programs in cycle 1. It's divided into 3 different kinds. These are small, medium, and large. Small programs only have 25 hours. A unit of observing time is an hour on JWST. On HST, it's a orbit, which is 90 minutes. It's going to have medium programs between 25 and 75 hours, and large programs are greater than 75 hours. And that would be a very expensive set of observations. Now, all of these observations are split up into different categories. There's exoplanets and disks, there's galaxies, there's intergalactic medium and circumgalactic medium, large scale structure of the universe, solar system astronomy, which I found interesting. It's going to look at stuff here in the solar system, stellar physics, stellar populations, and supermassive black holes and active galactic nuclei. These are all the different structures. This is for uh, general observations. Here is the guaranteed time observations that they're going to be doing, and that's broken up into these categories. I won't read all of these. Brown dwarfs, deep fields are going to be in here, which is really good. It makes sense that this is part of the guaranteed time observations. What they don't give you is lengths of time on these, but I'll go through some of these more interesting ones in just a minute. Extrasolar planets. That it's going to be looking at, which I think is uh, going to be cool. It's going to be looking, for example, here's one looking at the thermal emission of TRAPPIST-1b. Anyway, so this is their guaranteed time observations, and then there's going to be director's discretionary time right here. This is what they'll be using. This is the observations they'll be using for the under that, and that's also broken up into various categories. Let me collapse all. And these are the different areas that they'll be looking at for director's discretionary time. So let's take a look at some of the what I found were interesting ones for general observations. There's a lot here, and I'm not going to be able to go through every observation, but they're all given an ID number, and they're all in sequential order. Now, I did find this PDF that is an abstract catalog of the entire cycle 1 observations, both general observing and guaranteed time observations. And it seems to be listed in order of ID. There's this 4-digit ID, and like here's 1549. There isn't a 0 as far as I can tell. So I think they start at some number, and these won't be sequential in order of their ID. I don't think. I think these ID numbers, and I don't know for sure, but I think these ID numbers are just assigned at the point of proposing. And then you would be given a slot of observing time based on those other criteria I told you I told you earlier, which was where to go? What? Oh, scheduling observations right here. The prime this statement here where it schedules observations. They will schedule these observations to maximize overall efficiency. And that's a vague statement, but it means, all these things I mentioned earlier about where it's pointing and all that other kind of stuff. So, looking in the exoplanets and disks category, one of the more interesting things that I found earlier, and we found this in a really quick search of some of the other um, just doing a quick search on another hangout, was they're going to be looking at TRAPPIST-1D and looking at its atmosphere. Here, I'm sorry, TRAPPIST-1C and looking at the presence of an atmosphere. It's going to use 25 hours or 24.9 hours of observations. And they're going to be, if you click on the ID number, it pulls up the details of you know, you can get the PDF file and on all that kind of stuff of what it's going to be looking at. So that's one interesting thing. What happened to my? Oh, there it is. Okay, so so that's one interesting thing I thought it was going to do. It's going to also look at water spectra for rocky planets. It's going to look at WASP 121b. It's an ultra hot Jupiter. I think that's going to be pretty cool. It's going to be looking at the cloud composition and origin of the reddest known substellar companion of HD 206-893b. It's going to take 2.5 hours to do that. So these are there's some of the highlights of what I liked about what they're going to be using JWST for exoplanet research. Let's see what they're going to do. I'm still going through this, but let's see what they're going to do with black holes, because somebody was talking about that earlier. So let's see. Diagnostics at Cosmic Dawn, closing in on the launching states of AGN outflows, feedback around supermassive black holes and dusty nuclei. Look at this one, 65 hours of observing a comprehensive JWST view of the most distant quasars deep in the epoch of reionization. 65 hours. Now, this is also, it's called prime hours and parallel hours. Parallel hours, I found out, means using more than one instrument. So if you remember this right here, where I showed you all the different Webb instruments, you've got NIRSpec and NIRCam. Those are a lot of time going to be used in parallel at the same time. So a parallel operation means using one or using two or more of these instruments right here. And this is going to be using 8.6 hours of parallel observations. And here's the instruments they're going to use. They're going to use NIRCam, MIRI, NIRSpec. So 3 different images or instruments are going to use. By comparison, this next proposal, unveiling stellar light from host galaxies, Z about 6 galaxies, is going to use 16 hours almost of NIRCam only. So it's primarily single observations, and when they do have 2 of them here, is probably in sequence. They're going to use NIRSpec and then MIRI after that. This is one interesting thing. What I don't understand in this one is, it says the ultraviolet output of Sagittarius A star, but it doesn't have any ultraviolet instruments on board. So this may be a case where it's doing follow-up observations of something that is doing UV observations. But let me look at an implementation. Nope. I can't find it right now. I'd have to go look probably at this and find it and then read the abstract, because for some reason it's not showing me the abstract. So, all right. Where'd it go? There it goes. All right, so that's some of the stuff they're looking at with supermassive black holes. Let me see if I can see anything that catches my eyes here. Zooming into the monster's mouth, tracing feedbacks from their host to circumgalactic medium, about Z3.5. Going to be using NIRSpec for that. Let me also point you to this. This is a Twitter account that you need to follow. It's called JWST Observer. I don't know if it's going to be like what they do with HST. HST currently has a Twitter account that you can follow that will tell you where it's pointing and what it's taking observations of, along with the proposal ID that it's observing. I think JWST Observer is going to do the same thing. Obviously, right now there's not a whole lot on this account, but stuff about the launch, things like that. But this is an account that's managed by SDSCI and provides astronomers with the most up-to-date information, news, and events related to observing with JWST. So I have a feeling they might use this account to tell you where it's pointing when it moves from one thing to another. So follow this account, and you get a lot of, hopefully, I think, timely observations once they start, which will be a while. So, okay. Back to general observing programs. Quasar feedback in action, AGN feeding and feedback of NGC 4151. Unveiling the nature of CID 42, the best candidate for a gravitational wave recoiling supermassive black hole. So in most of these are using near spec and near cam for their observations as I scroll through here. So a couple of people are using MIRI, the mid-infrared instrument. So that's some of the supermassive black holes and active galactic nuclei. Let's see what they're going to do with the solar system. Let's see. There was a couple. Pluto's climate system with JWST. It's going to be doing that for 23.4 hours. It's going to use the mid-infrared camera and near cam, the mid-infrared imager, I mean. So if I click on that, why doesn't it have the... You would think you would have the abstract in it, but I can't. Oh, it is. All right, the New Horizons 2015. Boy, you had to really go there, didn't you? Click down into it. With the Pluto system unveiled a remarkably active world with a highly variegated surface and chemically rich atmosphere and extensive haze. Near cam imaging will map the albedo and methane ice distribution and resolution comparable to HST visible imaging, providing key tests for volatile transport models. Mirror imaging, 6 visits, 4 filters, will yield separate thermal light curves of Pluto and Charon, determining the surface thermal and energetic properties and further constraining Pluto's distribution of terrain. So that's looking at Pluto. I wish I didn't have to keep clicking so much. Where'd it go? Solar system astronomy. Variability and abundance of M-type asteroid Psyche. So it's going to be looking at that. That's that asteroid that has all that stuff on it that's supposed to be worth trillions of dollars. Pushing the envelope of JWST discovery space, measuring the insoluble organic matter and polycyclic aromatic hydrocarbon content of Comet 9P Tempel 1. Main detection of volatiles from a main belt comet. We're going to be looking at Hale-Bopp. Let's see. Trace gases in Titan's atmosphere with JWST MIRI. That's interesting. They're going to be looking at, they're going to be using MIRI to look at the atmosphere of Titan. First near IR spectroscopic survey of Neptune Trojans. So these are all things it's going to be doing within our solar system. Large-scale search of the universe. That's what interests me. It's going to do a cosmic origin survey. Look at that, 200 hours of time for these early universe observations. The first observations of ionizing luminosity of galaxies within the epoch of reionization, 22 hours. Answering the most important problem in cosmology today, is the tension in the Hubble constant real? 25 hours on that. Let's see, a definitive test of dark matter paradigm on small scales, almost 39 hours on that, 61 and a half hours on the spectroscopic survey of biased halo in the reionization era, a JWST quasar legacy survey. And then 25 hours on absolute brightness measurement of extragalactic background light using Galilean satellites, eclipse occultations. So This one's a big one for me. I'm interested in this. A lot of stuff coming out of here um, is going to be interesting to me. And then, of course, they've got some of the first galaxies. Oh, Dan Coe. So Dan's got some time, 11 hours almost, to look at a triply lensed. He's a gravitational lensing guy. Z equals 11 galaxy. 11. Okay, that's far, way, way, way far back than what Hubble can see. Hubble's maxed out at about 8 or 9. It can get a little bit further with gravitational lenses. Let's see. Achieving a revolutionary panchromatic view of early galaxy growth using near spec observations of 12 massive galaxies with ALMA-derived redshifts. 35 hours is going to be looking at galaxy protoclusters as drivers of cosmic reionization. But see, notice how all the time goes in some of these early universe observations. 46 hours, 187 hours is going to be used to look at public release imaging for extragalactic research. That sounds really vague, but 187 hours, 94 of which is parallel. That's a lot of JWST time. Deep spectroscopic insights on star-forming galaxies, 2.5 billion years after the Big Bang. That's 74 hours. So you're getting an idea of what they're going to be doing with this thing. Here's 121 hours. The Webb Deep Extragalactic Exploratory Public Survey, WDEEP. I wonder when they're going to do that one. Feedback in low mass galaxies from cosmic dawn to dusk. Now that sounds cool. A pathfinder of JWST spectroscopy, deep, high spectral resolution maps of galaxies over between Z equals 1 and 6. 75 hours devoted to that. Man, this is a lot of stuff coming down the pike. This is all after that it gets commissioned. Panoramic, a pure parallel wide area legacy imaging survey at 1 to 5 microns, 150 hours using NearCam. Wow, that's going to be amazing. And this is just all into the category of galaxies. So, and you can see all the different categories that are going to be going on. So you need to go to this website, check out all of the general. That's the general observing. I'm not going to spend a lot of time because I've been at this a while, going into director's discretionary stuff, and then there's guaranteed time observations. All of these things you can explore yourself. stsci.edu, and you just go to just do a search on JWST observations, and you'll get there. And vibe through. So let me get to a couple of comments. Hopefully, Tess might be able to find a lot more interesting targets for JWST. Yes, that's true. Also, JWST is going to be getting involved in the Event Horizon Telescope as well. It's apparently the Sagittarius A star black hole is flaring, and it flares in the infrared. It's one of the few supermassive black holes that do flare, and JWST is going to be looking at that flaring and try to give them a sense of how it'll affect their observations when they're doing the Event Horizon Telescope. So it'll be involved in that as well. Let me see here. I'm going to Discord. Got a couple people. Oh, okay. Let me hop in. All right, I'm in. So in case you don't know, one of the things that we're doing here is if you're on the Discord server and you're in the live stream voice channel, I can patch you in and you can say things to me, and we can talk like a call-in show. So Tony and is it Paradogs? Yeah. If you want to talk, you can. You don't have to. Your mics are muted. Thank you for that. And if you do say something, it won't go live. I have to push the button here. But if you do want to say something, then by all means, and I will push the button. So in the meantime, I'll read chats. Just for entertainment, what will happen if the JWST finds heavier elements like oxygen or carbon in the first stars? I know this is impossible, but just imagine what this would cause. Yes, Ebone, it would mean that we don't know how stars form. So that would cause a lot of problems. Um, all right, analytics group. I just calculated that with a life of 10 years, 1 hour of JWST time will be $114,285 USD. So what did you do? Take the number of hours in 10 years and divide that into $10 billion. Is that what you did? I suppose that's close enough. I mean, there's probably a lot more. Yeah, that probably is about right. Oh, hold on. All right, now you're live. Go ahead, say it again.
Yeah, that's still a bargain.
Yeah,
I
114,000.
mean, yeah, research.
Yeah,
You
yeah.
know, how do you put a price on research?
Well, that's just it. I mean, yeah, you build the 30-meter telescope on the ground and you look at certain wavelengths. There's a lot of ways you can do this, right? You could say dollar per nanometer or something of bandwidth that you can see through the telescope. Lots of ways of doing it. But yeah, that sounds about right. 100. I mean, if that's what he did, 10 years uh, times 24 hours in a day times however many hours in a year, and divide that into and multiply that by 10 and then put that into the total cost of the project. Yeah, it's probably you come up with a really big number like that. I wonder what do the same thing for Hubble. Although then you'd have to actually no, wait a minute, you're not quite right, because don't you have to also amortize that over the life of the mission? I don't know how that works. I'm not an economist type. We need Econ Greg here. He'll tell us what the right way to figure out what it costs is. Let's see.
Include operational costs,
Huh?
apparently.
What's that?
If you only took the $10 million, that doesn't include the
No, it does
having.
actually. The $10 billion+ figure does include operations. It costs like $9 billion to build it, and then for 10 years of operations, I think adds another billion to it. So I think that 10 billion number includes operations.
Oh,
So,
okay.
and do you also take into the account science's salary for 10 years? Uh, Yeah, that's true. You have to add their time, right, to it. Um, One thing I thought was interesting though is that you're given grants. If you're awarded JWST time, you're awarded money to pay for it. So that's got to be included in the $10 billion budget too, if it includes operations. Commissioned by Space Force, NASA, JWST, do you receive a crew member certificate or commemoration medallion? I want one for fun. You can make one. Just make one. Nowadays, astronaut wings are, they're not given out by the FAA anymore. At least not if you fly on Jeff Bezos's space penis. You won't get a set of wings for that, because I guess it's not special enough. I read that somewhere.
I know where you can get a Space Force badge.
Okay.
You go to the Netflix online store.
Okay. So in
For the
15,
TV series Space Force.
yeah, but okay, but I think you were saying something about JWST one, but maybe
Yeah,
a badge,
yeah.
a badge, I
Oh
guess.
well.
So in 15 years, will JWST be a useless piece of space junk? Maybe. It's a hell of a way to look at it. Why you gotta be that way? Why you gotta be so negative?
Perhaps we'll have
I
either
guess.
manned missions privately or automated drones to repair things like this, or to bring them down and repair them.
Yeah, you mark my words. After 10 years of JWST operations, we're gonna all be saying the same thing about it that we were about Hubble. Oh, we can't let it die. We have to go save it, bring it back to Earth. And
Yeah,
who knows where we'll be in 10 years.
put it in a museum or
I do believe that we'll have in 10 years the ability to repair remotely these satellites and space telescopes, and I also think we'll save Hubble. We've got about what, maybe 10 years, I think, on the
Mm-hmm.
outside of Hubble before it deteriorates. Just push it up into a higher orbit to buy yourself more time, and then I think we'll have that ability in 5 or 10 years. I don't see why not.
Now I'll go back to what I was asking before, regarding the time that certain people get for certain projects. Would you not have to look at a certain area of the sky so to get a better image of the early universe, or the furthest that it can go? Or am I thinking too visually?
Yeah, if the Hubble deep fields have taught us anything, and they've taken almost a dozen now,
Yeah.
that the very distant universe looks more or less the same everywhere you look. So so that there is no preferred direction in the universe, I guess, is what I think we've
Yeah.
learned from this. So
But
regardless
would
of
you
where
have
you
to
learn,
stare at
the only thing you'd have to worry about is maybe staying away from the center of the galaxy, just because there's so much crap in the way. It's probably
Yeah.
better to be looking at the early universe now during this time of year, when
Probably.
when we are facing away from the center of the galaxy and looking
Yeah, sort
toward
of
the edge. So
on the plane of our solar system, it would be up or
or up.
towards the edge of the galaxy.
Or you could look up or down, but you need to be careful, I think, with that, because of the orbital plane of the solar system is more or less, I think, aligned with the plane of the galaxy. It's not exact, but
Yeah.
and so if you look up, you also don't want to be going towards the sun in any way. Uh, so
All right. I thought the sun was.
well, part of this that I work on, I didn't work on any part of it. I worked at the Space Telescope Science Institute for 5 years. Hubble was still in operation. JWST was still being built. I knew and met a lot of people working on JWST. I met the project scientist, Massimo Stiavelli, and all these other people who were involved in the project. But I left there in 2016, so that would have been 7 years ago or 6 years ago, and JWST was so far from being launched. So I did work with people who worked on it, but I didn't work on the project itself. So that's the answer to that
So
question.
you could get an interview with you, ask them nicely.
Yeah.
Tony, there's
Yeah.
something I want to point out,
Okay.
and I don't know if that's clear to everybody, or maybe it's just painfully obvious, but how James Webb is going to be looking at is perpendicular to the orbit of the Earth. It's not looking straight out, but it's looking at 90 degrees, and it can rotate 360 degrees along that, but not. So its viewing area is constrained.
That's right.
Yeah.
Okay. So but so it's aligned at L2. It follows along as the Earth goes around the sun, and the orbit of the Earth will dictate a large part of what part of the sky JWST can see at a given time. That'll also have an effect on what gets scheduled when.
Yeah.
So
Yeah.
okay, I'm just scrolling through here. Do you think? Did I already read this? No, this is from Sarah. Do you think they will use the telescope for something extra if they get it ready before the telescope alignment complete step, like how they got sun shield tensioning finished earlier than planned? Maybe. I don't. I think the cooling time is still going to is pretty set.
Yeah.
So there was one thing I wanted to read to you though. So I wonder if I can find it. I came across so much interesting information. Oh, what this I felt. Let's see. There was a question in here in this fact about can you Oh, what if there was a surprise, a wonderful, this kind of is in line with your question, Sarah. What if there was a wonderful, surprising event, like a bright comet, an NEO, or a collision of a comet with Jupiter? And the answer is that's called a target of opportunity, and they can be routinely handled in as little as 2 days. The observatory can slew 90 degrees in under an hour, and will routinely send commands to Webb twice a day. I thought that was interesting. So if if you see an unexpected event like a transient event in the solar system, in as little as 2 days, they can go handle that. Maybe they could, if they really wanted to get it faster, they probably could. And I thought also it was interesting that the observatory can slew 90 degrees in under an hour. So that's pretty cool too. A lot of cool stuff in these facts. So just keep digging in and reading them. One of the questions
But
is
got
it too
to
late
keep
to
the
change the
sun
hardware
shield
design? Is-
towards the sun. That's the only issue.
Right. You don't want to be pointing anywhere near that.
Yeah, which
Or
is why
even getting it so that the instruments start to warm up. Is it too late to change the hardware design? Yes, much too late. The telescope mirrors are finished. This was obviously written a while back, but yeah. So I thought that was pretty cool. Then it's
last year.
So what you're talking about, Sarah, is a target of opportunity, and they are set up for being able to deal with that within certain constraints. So I think it's pretty cool. Let's see. And latest group is commenting or asking the ultraviolet spectrum can be redshifted to infrared because it's far away. That's correct. Let's see. A comment from Meme Dog Lol is surprising how much solar system work is going to be done. Not as glamorous, but there are so many unexplored objects. I think we could get exciting results. Yeah, it's cool that they are, going through a lot of this solar systems. They're keeping all the interesting things. I think there are 6,000 hours per year. I read that somewhere in the FAQ that is allocated for JWST observations. And or per cycle, 6,000 hours per cycle. This may not be a calendar year. I don't know how many hours are in a year. 365 times 24. I guess we'd have to do that. So it's per cycle is how many 6,000 hours per cycle. Believe in Jesus. Okay, let's see. Trying to get through reading some comments. You guys. So this was a hard one. I knew someone was going to answer this. What is the first target it will observe? And I really wanted to be able to answer this question, but I couldn't find it. And I think that's the reason is because it's not been determined yet. There is an algorithm that's going to be run when science observations start. A lot of it depends on when decommissioning ends and where in the sky James Webb is when that commissioning ends. They have a rough idea of all this now. And what will they decide to then go on will depend on, they're just saying to maximize efficiency. And also they want to get through the guaranteed time observations, the GTOs, because they have to get through those, your guaranteed time on these observations in the first 3 years of the mission. So they'll probably get
as
into those
little
first.
time as possible between rotation as well, so that the camera doesn't have to move at all. It just sails along merrily.
Yeah.
Yeah.
Why don't they just add a few extra gyros to start in the future? Like, a lot of people are worried about spare parts and redundancies, things like that. I'm sure all of this was considered, and then you have to balance what these redundancies. How would you switch them out? How would you switch out a pair of gyros, for example? And so, in the case of Hubble, astronauts went, took out old ones, put in new ones. How would you do that in this case? So even if you had them on board, how would you implement them? And there's that question. And finally, we talked about the gyros. They're this bearingless design
Yeah.
that has millions of hours of life in them. So that's one way to mitigate the need for those. And of course, if they do go
And
wrong.
also, we'll talk about all these extra gyros, a camera, things like that, you know. There's one little thing that you forgot, Tony.
What?
It all adds to the fuel.
Yeah. Yeah.
More fuel.
Yeah. The weight is a big deal too.
Yeah, and then you've got to add more fuel for that fuel. You know.
Ebone, I guess we have not talked about all the technology developed for JWST that will be used to our advantage. If you did, I missed that hangout. Yeah. So here's the thing I think is going to come down as one of the biggest spin-off technologies for amateur astronomy. Okay, this is going to benefit the amateur astronomy hobby. It's those micro shutters on NearSpec. NearSpec has these shutters on board that you can open and close. They cover a pixel. They're like, I don't know, so many microns big. And you can open and close each one of them individually to cover their coronagraphs that basically cover the light of a star so that you can see the very dim light from the planet next to it. That technology, I believe, is going to trickle down, and we're going to start seeing this in off-the-shelf commercial grade astronomy CCD cameras, so that you can block out yourself portions of the chip that would allow you to get more signal from faint things in that same field of view. A very bright star can really saturate your CCD and cause a lot of noise and bleed through and everything else if you're trying to dim something very if you're trying to image something very dim next to it. A good example is the Horsehead Nebula. The Horsehead Nebula is right next to Zeta Orionis, and on certain telescopes, Zeta Orionis is too bright, and you need to get it out of the field of view. And luckily, you can relatively easily with the telescope, and so that you can image the Horsehead Nebula part. You wouldn't have to worry about that with one of these shutter systems. So I think that's going to be one that comes up. So. Okay. Astro Spy, I'm going to leave this. Hello, fellow nerds. It scrolled on me. Let's see. I'd love to have a telescope with hexagonal mirrors that you can just add them as you need them. That may be another technology that comes off of this. These segmented mirrors. Now we already have them in ground-based telescopes like Keck, but I don't know. Maybe that'll be more common. I don't know. Charlie is saying, actually, that tech has been around for some time. The micro shutters, the micro mirrors that are used in some video projectors, at least 10 years old. Oh, okay. Well, these are shutters, not mirrors, but maybe they do the same thing. Anyway, that's just one technology I thought of. I'm sure this idea of using beryllium is also going to be something that you can use in a lot of things.
But beryllium's quite rare on Earth.
Mm-hmm. Jammin, what are the Webb cables pulling out the shields made of? Have they been used before in space? I don't know the answer, but I can tell you that they are at least space qualified. What's his name? Paul Geidner, I think, is the project manager at Northrop Grumman on this mission, and he was telling me that the every nut, bolt, hinge, cable, everything that's used on a space telescope or a space hardware at all is qualified. It has to be something called space qualified, which means that it either has to have worked in space before or has gone through a certain testing regimen that would qualify it as being used in space for the first time if it's a brand new technology. Something like a cable, I could imagine the ISS having had a lot of experience with cables, and so there might have been something space qualified they could have used in that sense. So I would say that while I don't know if it's been used before, I would say probably, and it would probably be something that's but it most certainly would be space qualified, whatever the cable is. So, all right, guys, you guys want to say anything else before I head out? Peter, you got any more comments? Tony, Paradog, you got something to say?
No.
You just want to listen.
Just hoping everybody had a lovely human decided Earth birthday.
A A human
or
decided
New
earthquake?
Year, as the majority of people call it.
What? Oh,
I was hoping that everybody had a lovely human-defined Earth birthday.
human-defined Earth birthday.
New Year.
Oh, God, that took me a while. Okay, a human
Yeah,
defined. Oh, because it's an arbitrary point in the calendar.
yeah.
I see, and it's human decided. Right. Okay. Yes. Birthday year. Yes. Okay.
Yes,
Yes. I had
Earth
a good one.
birthday.
I had a nice one. It was uneventful, as all of my New Year's are. I don't tend to do
Uh,
much except
Same.
stay
Yeah, I
stay away.
watched Jules Holland, and then I expected to see a Kaylee from Scotland, but there wasn't any on this year because of our restrictions.
Okay.
I
All right.
think.
Keep looking up.
Keep looking up. That's right.
Yeah.
Keep
Don't
looking
look
up,
up.
or don't look up.
Yeah.
Yes.
Go see it
Yeah, it's
now.
good movie. I need to check out this other one. What darn it? What did you say it was? The
Stowaway.
Stowaway. Thank you. I need to go check.
Yeah, it's very good. It's on
What's it on?
Netflix
What's it?
as well.
It's an okay. Good. I'll check it out. Stowaway.
Yeah.
I'm gonna write it down, or I'll forget it.
Or it was.
All right, I'll check out Stowaway and let you know what I think of that. I will be back next week on Tuesday. And I think this will be my last JWST hangout for a while. I've kind of done all I can do on it at the moment. We kind of all the other stuff that's out there, you can follow along on NASA's website. They're going to have, when it's fully deployed, which will be by Saturday, we'll know that, and then it's just going to be commissioning, and I'm sure there's going to be lots of milestones that will they'll televise there, or at least live stream. And I'll check in periodically if there's something interesting. We'll do another JWST live stream, but I think it's going to be it for me on JWST for a while. I want to turn to some other things that I want to talk about. So other topics,
Old
astronomy.
JWST out.
Yeah. Oh, you're asking about this shirt. So there is a company. I get these emails. Let me see if I can. It's a NASA contractor. I'm on some kind of email list. Let's see if I can promotions something. NASA JWST. It's called nasapromo.com. This is where
Can you hear me, Tony?
Yeah. So let me just get this out real quick. So it's called nasapromo.com, but when I click on the
There's
the thing,
a lot of delay, so this is probably not going to work. But
oh, okay.
I can hear you, Faradog. Mute the stream.
If you mute the stream, you probably won't get the delay.
Yeah, and listen to whatever's here.
So here, go to this website and get on their mailing list. This is only if you want to. Anyway, I'm on their mailing list. If you go to that website right now, you won't see anything. But they keep sending me stuff. Like with missions happen, I get this shirt, and it came with a hat. It was like reasonably priced. It wasn't a big deal. That's where I got it from. You can make your own too in this thing. Just go to Teespring and make your own. That's what I did that as well.
Yeah.
Okay. I think that's it. So did you want to say something, Paradog? No? Just wanted to see if I could hear you. All right. For next time, join the Discord server on Deep Astronomy.
But I don't know how to not have this delay. I have to figure it out for next time. Sorry.
All right. You've probably got two things going on. You probably have the stream going and you're listening on Discord. So you want to mute probably the stream because it is going to be delayed by about 30 seconds.
Twitch or YouTube or whichever one you're watching.
Yeah. All right. So, okie dokie. All right, guys, I'm out of here. I will see you guys on probably Tuesday. I'll try to figure out what I'm going to say then. Hope you guys have a good weekend. Thank you all for joining me. Thank you for watching and listening and talking. Go to Discord, Deep Astronomy Discord server. The link is in the description box. Join it up. And if you come in before the next stream, we'll approve you and you can join the live stream voice channel and talk with us on it. So thank you. Talk to you later. Keep looking
Up.
Go ahead, Peter.
Or don't.
Or don't. Do. Do look up. Do look up. It's better than not looking up. Keep looking up. Bye-bye, guys.
Bye. Oops. What am I doing?